Alright, this is the slide we were in the last video, the Chapter 19B. This one is, of course, part C, or it's going to be part C. Alright, so anyhow, this is one of the things that we've noticed is that when you have 0.08 times the mass of the sun or greater, of course, it's going to become a star. So that's basically 80 times the mass of Jupiter or greater. These things are going to be hot and dense enough for nuclear fusion to take place. But suppose you're below 80 times the mass of the sun, the mass of Jupiter. If you're below that, that's ends up as, what we would consider a failed star, or what's more commonly it's called a brown dwarf. All right, so these brown dwarfs, we have actually detected them throughout the galaxy. So let's all right. So here's a phenomenon that we want you to understand is this stage 1, 1 through 7 is happening simultaneously in certain regions. Especially in regions where there is what we would call stellar nurseries, star nurseries, like the Orion Nebula. So you're having all sorts of things happening at the same time. There's fragmentation going on, so you're going through from stages 1 through 2, and then you're getting onto the main sequence in stage 4, and then there's lots of stuff happening even at the same time with some of these stellar nursery regions in the galaxy. All right, and of course we see these in other galaxies too. We can't make them out quite as good as we can. Like, for example, here's Orion, right? This is the belt of Orion. There's Betelgeuse. This is Rigel. That's the star Bellatrix. Anyhow, below Orion's belt is this region that you can actually see with the unaided eye. I know I've mentioned this before, but when you look at it with a telescope, there are new stars being born there. Okay, so all 7 stages are taking place there, and there are literally hundreds and hundreds, and perhaps even thousands of stars inside of this gigantic star-forming region. Right. You might remember before we looked at a picture of what's called the Pillars of Creation, which is another star-forming region. And again, all the different stages are taking place at that particular location. All right. This is notice this is a protostar that's around stage 5, and so we can take pictures of these, not in the visible, but in the infrared, and then we put false color in there to get to see what these things look like. All right, so let's see. One thing that happens that we've noticed when protostars form is that a lot of times they'll have really strong winds, and sometimes those winds will be directed in a polar manner, like a bipolar flow, so that they'll be above and below the direction that the star is rotating, and sometimes these are associated with strong magnetic fields, or they could just be wind too, like solar wind. There's particles coming off of our sun, but it's not like this. This is a major amount of material coming from these stars, and that has a profound effect. This solar wind in protostar, when a protostar is forming, what happens is that actually it tends to here's some more pictures. So here's an example right here. You can't see the protostar that's forming, but you can certainly see its effect, the effect of the wind on the surrounding stellar material, the surrounding cloud. Anyhow, these things have a profound wind. The wind has a profound effect in the region around what'll eventually become a solar system unto itself, right? Um, oh yeah, and that's one thing I should have mentioned is during the even before the protostar phase, there is in the fragmentation there are things that would certainly be considered like Jupiter-sized objects, or even anything up to about 80 times the mass of Jupiter, or even smaller, that form from these fragments, and the fragments will continue, to spin around the protostar, and then of course when it becomes a star, that'll be a planetary system around that particular star. All right, so all right. Here's an example of a brown dwarf. These are actual discoveries that we've made, actual pictures of these things. They're very difficult to see because they just don't emit a whole lot of energy, because there's no fusion taking place. They are hot. They're certainly not the surface temperature of like a star, but they do tend to be hot. Let's see, observations of brown dwarfs. Many faint specks in this stellar cluster of brown dwarf candidates. And like planets, brown dwarfs are expected to have star-like composition. So, all right. Let's see. Shock waves from nearby star formation can be triggered, and that'll get the original interstellar cloud to start collapsing. We mentioned this before. So what are some of the triggers that you can have? The death of a sun-like star. So when our star dies, it will there'll be this giant shell of material that'll expand out into space, and that's what they're talking about. So these are waves that of material, mostly hydrogen and other elements that the star has created, carbon, things like that, oxygen, and that'll go out into the surrounding interstellar medium, and eventually perhaps trigger the new star formation. And then certainly there are supernovas. These are really massive stars, much more massive than our sun, that basically explode at the end of their lives. And there's also within our galaxy, since we're a spiral galaxy, we think, and no one's proven this yet, but we're certainly we think that this idea of a density wave in spiral galaxies that starts in the center of the galaxy and rotates around and goes outward from the center of the galaxy, that we think that these things exist. People are still trying to prove that. I mean, it's wonderful to have an idea, but of course in science you have to actually test that idea. You have to perform experiments that will verify one way or the other. Another thing that can happen, and this we'll talk much more about when we start talking about galaxies as a whole, but there's really strong evidence that galaxies collide. Even the Milky Way it seems like there's parts of the Milky Way that have collided with other smaller galaxies. And so that galactic collision can even trigger some of these interstellar clouds to begin to collapse. All right, let's see. So you can have several generations of star formation. So you can have very new stages taking place at the same time. You can have older stars that have been born and been around for, let's say, a few tens of millions of years, or even older, right? And so let's see, because single interstellar path can produce many stars. So this is actually really important, this idea of the star cluster. All right, so the clusters are, when we look, like for example, the Pleiades, right? We studied the Pleiades, and there's another star cluster that's nearby. There's lots of them, but there's another one in the same region of the night sky called the Hyades. It's a little bit older star cluster. Anyhow, these star clusters, one of the assumptions that people make is that astronomers make is that the star clusters, the stars that are part of the star cluster, so they're moving in various directions, but they had the same origin, so they would have started in the original cloud of material, and then of course fragmented, and that's really the fragmentation leads to some of these clusters. So for example, they're talking about the Pleiades. There's the famous picture of the Pleiades, also known as the Seven Sisters. We need to distinguish these clusters that we find within the disk of our galaxy are called open clusters, and there are other clusters that are outside of the disk of our galaxy in the region that surrounds our galaxy called the halo. And those are what are called globular clusters. Right? Those tend to be very, very old stars. In fact, some more than twice the current age of our sun. In some of these, so there's a picture of a globular cluster. The globular clusters, again, much older stars. They're very metal poor. So these a lot of the evolution that's taking place in the disk of the galaxy, the stellar evolution is not taking place here. All right, so let's see. So now the difference between the HR diagrams of open and globular clusters, the globular clusters are extremely old, and then the open clusters are much younger, and you can actually see this from what's called the turn-off point. So, and we'll look at what that is. It has to do with stars that are on the main sequence. Remember, all the stars, eventually end up in the main sequence when they come to equilibrium, and will stay there for their entire life. And then they move off right as their hydrogen fuel supply is used up. Okay. So the point where, if you looked at a cluster of stars, let's see if they have a picture of it. What's this? This is the presence of massive, short-lived O and B stars can profoundly affect their star clusters as they blow away gas and dust. All right, so this is just a simulation. There's a nice picture of the Orion Nebula. And let's see, Eta Carinae is this huge star that we expect to blow up into a supernova at any time. I mean, it's, ever since people observed it, they in fact they thought it was going to explode. 150 years ago. It didn't do. It exploded, but not the kind of explosion that we expect from a supernova. We're still waiting for that to happen. It's it could happen at any point. One thing. So what I was mentioning is the HR diagram. So when you have let me go back to the star clusters. So a young cluster like this, if you have the main sequence, the stars way up here will leave the main sequence first, and so if you look at a cluster, the further the turnoff point is, the point where nothing above within that cluster, there's nothing above. Let's say this point right here where I have the mouse pointed. If there's nothing above that, then you can estimate the age, because we know how long stars, these stars will last, and if you don't see any stars that are further than, let's say, this point right here, then you know approximately the age of that cluster.